Patricia has worked in computing for a long time, won a prize from IBM long ago, worked in cybernetics. This is a lady that absolutely knows what she's talking about. But a fascination for her has long been physics. And she's not quite convinced that Einstein is right. And we're going to understand today that perhaps we do need to question things that we think are absolutes, but if we go beyond that, maybe we'll advance a little bit more. So I hope we're going to enjoy a whole new view of physics from Patricia Dean. Thank you.
Okay then, I hope you can hear me. If you can't, just keep it to yourselves and try and doze off. Yes, I'm going to be talking to you about the truth about Einstein and the mystery why he's been believed for so long and what new frontiers await you if you forget his myths, and they are myths. Yeah, I know, sharp into the take a breath. I have to say, it's about this point that any speaker who comes up here experiences a strong sense of panic, an overwhelming urge to run, which is why I've asked them to leave that door open. If I start to gibber or try and crawl onto the stage, please be sympathetic. I've only got about an hour to disprove Einstein, so I'd better get a move on, hadn't I? Now, as I'm talking about Einstein, you've got to expect some fairly scary mathematics and some really weird physics, and you're not wrong. Let's start with the scary maths, shall we? Deep, calming breaths, folks, deep, calming breaths. Here we go. Is that right? Do you believe it? 1 + 1 = 2? If I asked you, could you prove that? Those who said yes, shut up, I'm on. Or you can come and do this talk. It is true, but only because of the rules of the game of standard mathematics, sometimes called Euclidean mathematics, named after the ancient Greek mush Euclid, who started to formalize it back in 300 BC, or thereabouts, after breakfast. According to the rules that he set down, they're the sort of things you learned about at school without actually knowing you learned the rules. All the bog standard mathematics, multiplication, division, squares and square roots, the binomial theorem, differential equations, calculus. God. They're only true because of the rules in Euclidean mathematics, the definitions. The definition of what is meant by an integer. Whole number, 1, 2, 3, 4. What does it mean? They're defined in the axioms. The definition of a gap between successive integers. What is meant by that and what is meant by that. Only because of the rules of the game is that true, and it forms one of the major theories of Euclidean mathematics. But if you want to, you can change the rules. And there are people who do work professionally in non-Euclidean mathematics and non-Euclidean geometry. I never did this professionally, but I was taught how to do it. If you change the rules, you come up with different answers. My own personal best plus a pint of custard every alternate Tuesday. 1 + 1 = 3.5 plus a pint of custard every alternate Tuesday. I'm not kidding, I could actually prove that. I changed the rules and it changed everything. Totally useless, but great fun to do. Yeah, I know, get a life. But the point I want you to get from this is not that I'm a deeply weird person. Yes, I am. But if you change the rules, you can't use anything from the original set. Under Euclidean mathematics, we have multiplication, division, squares and square roots. What is the square root of a pint of custard? I don't know, and I invented the system. Please remember this, it's very important. If you change the rules, you can't use anything from the original set. Why do I say it's very important? Because Einstein didn't remember. Okay, let's get rid of that. Please notice I will be setting test papers later. Right, you think I'm kidding, don't you? Nope. Right, now then. Einstein set out to replace the existing science of his day, which means I've got to spend a little bit of time telling you something about that. What was there before Einstein? Well, basically, the answer was Newton. Sir Isaac Newton, 17th century philosopher, polymath, apparently world-class grump, extremely famous person. So famous that when he died in the early part of the 18th century, he became the first commoner ever given a state funeral. The second person ever given a state funeral was Nelson, 100 years later. In those days, you really had to work at being a celebrity. Yeah, yeah. Just appearing on Love Island didn't hack it back then. I think Newton might have tried it. But, right. Now, Newton was interested in just about everything. Motion of the planets, the workings of the eye, the motion of the tides, the nature of light. You name it, he was interested. But we're interested only in his theories of motion, generally known as Newtonian mechanics. What makes things move, what happens when things hit things in motion, how it all hangs together. Now, you will know some Newton, though you might not know you do. The distance an object travels is calculated by multiplying its speed by the time taken. Distance equals speed times time. If an object is moving at 60 miles an hour for 2 hours, how far does it travel? 120 miles. Fine. Now, when Newton was working, he was extremely precise. He was pernickety. He was hair-splittingly precise. And everything he did, he defined extremely carefully, all the elements that he was working with, proved it mathematically, proved it by practical experiment, and then described it all. In Latin, but you can't have everything. Time, for Newton, was unchangeable, unalterable. Couldn't speed it up, couldn't slow it down, couldn't alter it in any way. He likened it to a vast river, eternally travelling through the universe, unchangeable. Some things that Newton dealt with weren't quite as unchangeable. Nearly so, but not quite. Dimensions and mass, for example. For an object in motion, it didn't normally change its dimensions or its mass unless you applied a force to it. Force was something Newton was very keen on. Let's imagine there's a car here between us. Doesn't matter what the make is, doesn't matter what the colour is. There it is. It's got dimensions, it's got length, it's got height, it's got breadth. It's got mass. If the idea of mass bothers you, think weight instead. Weight is just the pull of Earth's gravity on mass. As you move out into space, you become weightless, you never become massless. Newton said the dimensions of the object and its mass do not change no matter how fast the object is moving, and in Newtonian mechanics there is no limit on how fast an object can move. 10 times the speed of light, 1,000 times, 1,000,000 times the speed of light. Newton set no limits on an object's ability to move, none. That car's dimensions don't change, its mass doesn't change until you apply a force. Let's ram it into that wall over there, that'll do it. That'll apply a nice force. Suddenly you've changed the length of the car fairly considerably, and you've rearranged its mass. You haven't actually destroyed any part of its mass. According to Newton, you couldn't do that. You might rearrange it, you might alter its state, but it was all still there somewhere. Okay, so dimensions with Newton couldn't change unless you applied a force, nor could its mass. One thing could change very easily, though. Oddly enough, that's speed. Without you applying an accelerator, without you applying a brake, the speed of an object depends on its context. Newton's very keen on context, sometimes referred to as the frame of reference or point of reference. The context. I shouldn't say, for example, that our car, when it was about to hit that wall, was travelling at 60 miles an hour. That's sloppy of me. And Newton's ghost would tap me firmly on the shoulder and say, relative to what was it travelling at 60 miles an hour? And what I should say, of course, is relative to the ground or relative to the road. I need to give that context. Here I stand, imagine me at a bus stop waiting in ever-diminishing hope for the coming of the blasted bus. They've rearranged it again, it's not there. But here I stand, waiting, and there's the car passing me at 60 miles an hour. That's another context. Because I'm standing still, that doesn't change the speed of the car. It's also passing the bus stop, another context. And again, it doesn't change the speed of the car because that's not moving either. But supposing our car is passing another car, and that other car is moving at 40 miles an hour. Relative to that car, our car is doing 20 miles an hour. Relative to that car, the speed has changed just by changing the context. And Newton says everything displays this character. It's always got variable relative speed. or velocity if you want to include direction. Velocity is just the speed of an object and the direction it's moving in. Right, so everything varies depending on its context. As one object passes another, its speed can change just because you change that view. Newton's principles were regarded as a scientific equivalent of Holy Writ for 2 centuries. In fact, we still use it. It was Newtonian mechanics that put men on the moon. And it's Newtonian mechanics that NASA used to send probes out to the planets and the moons of the planets. Not Einstein, curiously enough, Newton. Let's get rid of that a minute. Chat amongst yourselves and turn my back, will you? Just do it quietly. Right, now, I said Newton was the equivalent of Holy Writ. Until something rather weird happened in 1880, or the 1880s. A couple of scientists, one called Mitchison, the other one called Morley, as a result of which their experiment happens to be handily entitled the Mitchison-Morley experiment. Well, why not? It's a good enough title. They were setting out to prove or disprove the existence of something called the ether, which was the 19th century's equivalent of dark matter. It was supposed to be all-pervading in the universe, according to the latest theories back then. It affected how things moved. It was a means by which light was propagated through the universe. But nobody could see it. Nobody could touch it. How do you know it exists? Well, Mitchison and Morley thought they'd found the answer, and their experiment was intended finally to answer the question of whether the ether is or the ether isn't. To their utter horror, their experiment didn't give them any help in that at all, but it seemed to show that Newton was wrong. Yeah. Can't be. No, forget I said that. It appeared from their experiment that light moved at constant speed. That is, light did not display variable relative velocity. If light is passing me now, and light's pretty nippy stuff, so you won't really see it go, 186,000 miles per second or 300,000 kilometers per second, that's the standard running speed of light. If I'm standing here, light is pouring past me at 186,000 miles per second. It's passing that car, which is moving relative to me at 60 miles an hour, at 186,000 miles per second. No change. There's an aeroplane up there, which is moving roughly at 500 miles an hour in that direction. Light is pouring past it at 186,000 miles per second. How's it doing that? According to Mitchison and Morley's experiment, it seemed there's nothing you could do to vary the speed of light. It was always a constant. It was as if everything else in the universe was standing still relative to light. This was deeply weird and deeply non-Newtonian. What the heck did this mean? Bags of panic are what it meant. There were those that said the experiment must be wrong. Mitchison and Morley, who trusts them? It's got to be wrong. In point of fact, that does actually appear to be the case. I haven't time to go into that now. If you're interested in knowing about the Mitchison and Morley experiment, come and talk to me, and I'll explain why it probably was wrong. But at the time, they couldn't see a flaw in it. There were those that said, OK, something else is going on. Maybe this mysterious ether is somehow affecting the experiment, which gives you a problem because you still can't prove that the ether does or does not exist. But hey, let's not bother about that. And there were those who very, very tentatively said, OK, maybe Newton was wrong, but only in the case of light. Something weird about light. And there were those that said, and we hear here the entrance of Albert Einstein, that no, Newton was wrong. Not just slightly, completely. In 1905, Einstein produced a number of papers, 5 in total. Only 2 of them dealt with his wonderful new theory. His theory in the 1905 one, officially the special theory of relativity. We all say special relativity. He meant special theory of. If you do happen to want to read the original papers, you'll find them a reprint in here. All 5 papers, only 2 of them deal with relativity. I strongly suggest you don't read them, because that is a pig of a book. The mathematical proofs, yes, I do know, I have been through them. The mathematical proofs in there are chaotic, they're obscure, they're quite difficult. No, ignore that one. You can if you like. If you feel strong enough, come and talk to me and I will take you through it. Fortunately for us, in 1916, Einstein produced that. It's a simplified version of his 1905 paper. Think of it, if you like, as the Idiot's Guide to Relativity. Einstein produced the 1905 papers for fellow scientists and the rest. This is aimed at the man in the street. And yes, I do mean man. Women weren't supposed to be interested in that sort of thing back then. That book is a very valuable starting place if you do want to get to grips with Einstein. It's still not an easy read, but if you do work through there, and yes, you've guessed it, we are going to. Yeah. Sorry about that. If you work through there, you will find exactly what he was trying to do, and more importantly, why he shouldn't. But let's start from what you know about special relativity. And you probably do. Visualize the whole of relativity as an inverted triangle with special relativity down there and general relativity based on it. It's called special because it's specialized, limited. It deals only with positive linear motion, motion in a straight line away. General theory, which came about 10 years later, expanded that to cover all forms of motion. And I've just found I've lost my flipping... Oh, never mind. I did have a cleaner around here. I've dropped it somewhere. Never mind. Okay. What this means is if that is wrong, that inevitably is wrong because it's based on it. It's an extension of it. And right down at the bottom, really pointy end of it, a couple of equations. I used a bad word there, didn't I? Equations. Sorry, mates, the doors are all locked. You can't run away from it. You're stuck. Okay. We're going to be down there, and more particularly, we're going to be fossicking down in there. Right. I said you know about relativity, and you almost certainly do. You must have heard that Einstein said, in the special theory, that the speed of light was the limit to all motion. Nothing can travel faster than the speed of light, and only light can travel at the speed of light. And as an object moves, just because it moves, it loses length, it gains mass, and time slows down for it. Now this is seriously weird stuff. An object in motion loses length just because it's moving, and the faster it moves, the more of its length it loses. Nothing else is happening, no force is operating. Doesn't matter what the thing is made of, doesn't matter the strength of the structure, just because of its speed. I have here a piece of paper, which I will now perform a magic trick with. I will roll it up neatly into a tube. If I take a bar of iron the same length as that and make it move the two together at the same speed, they both lose length exactly the same amount. No crushing, no crumpling, they close in on themselves. A little bit like an old-fashioned draw telescope, they just collapse inwards. Even if the bar of iron is a mile in diameter, it loses length at exactly the same quantity as that, purely depending on speed. Wow. Depending on the structure? Nah. Depending on the strength of the materials? Nah. Take the Eiffel Tower for its base. Please, I think it's ugly. Turn it inside and make it move. It's a very strong structure, which is why it's lasted as long as it has. Regardless of its structure, regardless of its composition, it will lose length just because of the speed at which it's moving. Ooh. At the highest possible speed any object can attain, and remember, nothing can attain the speed of light, just below the speed of light. At the highest possible speed anything can attain, its length has reduced not to a point. A lot of people think it says a point. It doesn't. It says to a thin smear. Nothing happens. The cross-section doesn't change. It's just closed in on itself. How on earth does it do that? Well, Einstein, bless him, never explained. He never fully explained his theory. And that by itself is not bad, except it is bad for people who come after and try and explain what the heck is going on. He didn't explain how this physically happens. And mass. Mass increases? Mass is just the total amount of stuff in an object. My mass as I stand here, and anybody who calls out my weight, I shall see to them later. My mass as I stand here is made up of flesh, blood, bones, clothing, jelly stuff in the eyes, jelly stuff in the brain. If I start moving, Where does the extra mass come from? Which bit of me is there now more of? If I'm eating an egg and cress sandwich as I walk along, is now more egg in my egg and cress sandwich? Where did it come from? And just as more important, where does it go to? Because the theory says that as an object slows down, if it does, the length returns to normal, the mass returns to normal. Wherever that funny mass has come from, it's gone back to. Ooh. Even, ook. And time slows down. We no longer have the universal Newtonian idea of a river of time. Everything now has its own individual time, and the time of a moving object slows down for it the faster it moves. So just before the fastest possible speed, sorry about that, it's the gin. Just before the fastest possible speed, time for the object has stopped. Not for anything around it, just for the object. It's stopped. Some theory, you know. Really a weird theory, but okay, if he can prove it, he can prove it. And even awkward old tarts like myself have got to accept it if he can prove it. I wonder if he can. Okay. His proof is in here. It's actually hidden in Appendix 1 of this, because he tried to keep the complicated stuff away from bothering other people. You will find exactly the same thing is in there. This is a simpler version of that. So we ignore that for the time being, and I'll try and leave it on a train somewhere. Now, when Einstein started to work to prove his new theory, he said there are two fundamental assumptions you have to make. The first is, yes, the speed of light really is a constant. And he identified it, large capital letter C. Wherever you see that in Einstein's work, that stands for the constant speed of light. We'll kind of come across that several times. Capital letter C stands for the constant speed of light. He also said, and this is something I think very few people know, that you have to redefine the whole idea of what motion is. Einstein says, motion is defined by our experience of it. Pardon? Our perception of it. That's not much better. Our observation of it. Literally, seeing defines reality for Einstein. He said the same is true for all physical laws. All physical laws require human sight to define them. He never said what happened if there wasn't an observer. He never said what happened if there wasn't light to see by. As I said, he left gaps all over the place, and these were some of them. If you go back to our case where I was standing here by the bus stop, there's the car. If I'm not there in Newtonian mechanics, the car's still moving, still doing what it was doing. I don't have to see it, I don't have to be present. In Einstein's mechanics, I do, and I have to observe it. Which means there has to be light as well as an observer. Okay, question, Mr. Einstein, sir. When the solar system was formed, who was there to observe it? Didn't it move? He doesn't explain. In the depths of the ocean, don't things move? There's no light down there. Light can't penetrate. Things move. How? Einstein didn't explain. Okay, but as I said, gaps in a theory by themselves don't invalidate the theory. They just make it tricky. Bear that in mind, please. The magic word there was redefine. Think back to what I said about 1 + 1 = 2. You can redefine the basic rules if you want to and end up with 1 + 1 = 3.5, but you can't pick and mix. You can't take anything from the original set. You really, really can't. Okay, let's watch Einstein, she said with a certain amount of trepidation, prove his theory. Deep calming breaths, folks, deep calming breaths. He says, in here, let's take the simplest case of motion. Simplest possible example. Don't want that one, I want that one, thanks. A train moving along a railway track. Here we come, graphical representation of a train and a railway track. Here's the railway track. Chick, 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 chick. A wobbly one. I'm going to call that X. So that should be X. It starts there, ground zero. It's a perfectly stationary thing, so mathematically speaking, and sorry about this, talk amongst yourselves if you're not happy with this. I would define that as x equals straightforward numerical sequence, no motion, it's just lying there, gathering litter and freezing solid in winter. And on it, there is a train. If you like, make Thomas the Tank Engine noises while I do this bit. There's the back of the train, and it's sliding along here, and we're going to call that x bar, because Einstein did. That's all there is to it, except the train is moving at velocity v. That just means any number you like. Velocity v is a mathematician's way of saying whatever, any speed you like. That's what Einstein is going to base his proof on. That's what he's going to work with as a definition of motion. And he goes away and does it. He says he wants to produce a mathematical relationship between the two. Hang on, this is the point at which this all falls over. Up and around. And that's what he comes up with. Please don't scream. You don't have to understand that, but these are the two key equations that actually define special relativity. That is the one Einstein says demonstrates that an object in motion loses its length. I'll come back to that. That is the one that Einstein says demonstrates that the time of an object in motion slows down. And the bottom part of both of them, that is exactly the same as that, shows, Einstein says, that if an object moves at the speed of light, actually it can't do that, it's impossible. And looking at that at the first glance, you think that was right, wasn't you? If the speed of the train matches the speed of light, then that becomes 1. And 1 minus 1 is 0. The square root of 0 is 0. And 0 divided into anything is a mathematician's scream of pure agony. It's impossible. Technically speaking, it's infinity. You can't do that there, here. It's an impossible number. Now, Einstein reads that to say, therefore, that can't happen, which is naughty of him, because that's not justified, at least not yet. It's quite possible for this equation just to have a mathematical limit. Now, what that means is there's an equation that can't be used beyond that point. If I wanted to have a cup of tea, I know I'm not allowed to, but I do, I want a cup of tea. Okay, let's imagine there's a cup of tea right here. If I wanted to, I could work out the temperature of the liquid in that cup of tea. I'd start out with the initial temperature, hopefully boiling point, take the volume of the cup, the exposed surface area, because that's where most of the heat's going to be lost through, the insulating properties of the cup itself, if I wanted to, the air temperature and the air pressure, and I'd end up with a nice little usable equation that told me over time how the temperature was dropping in my cup of tea. But if the liquid froze, I couldn't use it. Not that the liquid can't freeze, but I can't use the equation, because as soon as even a thin crust of ice forms on top of that liquid, the temperature gradient changes radically, because ice is a very good insulator. That's what I mean by mathematical limit. Einstein says that demonstrates the object cannot move at the speed of light. Not necessarily, not yet. There's a bigger problem though here. C. C stands for the constant speed of light. But where the heck does it come from? Hang on, is it still going to move? Yes, whoop, try again. Hang on. I'm an only an engineer's daughter, so I'm absolutely rubbish at comes to moving things. There is a train moving at velocity v and a railway track. Where's light come into this? He needs to get light to come into this, because his whole thesis is that light defines motion. So he has to get light in there somewhere. But how? If we turn to Appendix 1, almost fell on the ground, he tells us how. He says, hang on, pause, try not to drop this. A light beam is proceeding along the axis X, along that thing, in accordance with well, that's good, isn't it? He's got C. From there, he's going to start to build towards his equation. Hang on. Hold it. Does that look familiar to you? It should. Let me read it out to you. The distance an object will travel, in this case a beam of light, along the x-axis is calculated by multiplying its speed by time. Distance equals speed times time. That's Newton. Einstein can't use Newton. Einstein can't use Newton, can he? To which the answer is resounding, no, he can't. He double dog definitely can't use Newton for light. Why not? Well, I did tell you that Einstein reckoned the speed of light was constant, which meant light is non-Newtonian. That's a Newtonian formula for something which is fundamentally non-Newtonian. Einstein also said separately that the differences between his calculations and Newton's calculations only became apparent at high speeds. At ordinary low to normal speeds, you couldn't tell them apart. His changes were still happening, says Einstein, you just can't detect them, they're too small. Low speed motion, therefore, is fine for Newton. That isn't low speed motion, that's very high speed motion. That is actually the highest speed anything can attain, according to Einstein. If that is valid, Newton's formula is valid for light, it's valid for absolutely everything. But he can't use Newton for anything whatsoever. Why not? Because he's changed the definition of motion. He's changing the whole concept of what motion is. Motion is now no longer the Newtonian, it is what it is. That car is still moving whether I'm looking at it or not. It's now, you have to observe it to define its motion. And now, length is something that concertinas in and out. And mass varies up and down, depending entirely on speed. And time is now fluid and individual. None of those things fit within Newton's definitions. Therefore, you cannot possibly use Newton for anything in Einstein's world. He can't do that, but he does. Look what it does. Suddenly, the railway track has disappeared. He's now got the motion of light forming that lower axis. Weird. And Newtonian light as well. He then says, okay, the beam of light is moving along that axis, but it's also passing the train. That's X bar, which is for that. That's a very badly drawn X bar. Oh, tough. X bar is also now the speed of light, the motion of light, Newtonian motion of light, which is pretty weird. He's now got two Newtonian motions for things that aren't Newtonian motion. But he uses them. He doesn't explain why he thinks he can. He uses them. And he uses them for light in the positive direction and also light in the back direction. And after a bit of faffing around, only about a side and a half of that in Appendix 1, he arrives at an interim equation. Don't panic, don't worry, take my word for it, I can show you if you want me to, that is a very badly drawn B. A and B are two tricky little equations that he wants to find values for. That, Einstein says, is his interim. It's as far as he can get just working with light. That is derived from this, which means immediately you have to say that those two must be equal. They must cancel each other out. B divided by A must be 1. Because if not, he's just contradicted the equation he started out with. And in mathematical terms, that counts as an absurdity in large capital letters. You can't do that. If you find a flat contradiction like that, it means you've gone wrong. Badly. So B and A must be identical. Okay, whoop-de-doop. Einstein then says, okay, let's bring in the motion of the train. And what he says in the magic book is the train is moving relative to the x-axis at velocity v. That's the x-axis. Light. Einstein, he's forgotten what he's dealing with. I don't know how he's forgotten what he's dealing with. He has, and it's not going to be the first time or the last time. He's now got his train moving relative to light, which means the speed of light is not constant. It was a fundamental principle of his new theory that the speed of light was constant, which, if that's the case, light passes everything as if everything else is standing still. Nothing can have velocity relative to light if the speed of light is constant. And he's now got the train moving at velocity relative to light. The speed of light is not constant, folks. And the equation Einstein uses for the train, oh, what a surprise. It's Newton again. He can't, oh, I've said that. He's used Newton for light, he's using Newton for the train. He can't do that. He's also done something even weirder. He had that, let's move that because that's going to confuse you a bit, it's down there. He had said that was what the x-axis was, CT. He now said it's that. Something terrifyingly predictable is about to happen. What he does is he manipulates these to find a replacement for time there, and what he ends up to is V equals C. The train is moving at the speed of light. He can't mean that. Not even Einstein can mean that. No, he doesn't mean it. He's gone wrong. That is actually incorrect. He's made a number of mathematical slight hiccups. Einstein was a very, very clever man. Unfortunately, he was also a very accident-prone mathematician. And yes, I can prove it. And if you want to come and see me afterwards, I will. I will show you some of the full horror of what Einstein got up to in terms of mathematical failures. But this is the beauty of an example. He's got Newton, 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 and the speed of light no longer constant. He's also made a whole series of slight errors, which means he achieves that result. He doesn't actually write that down. He never gets that far, but what's on the page screams out that that is inevitable. Well, of course it is. He's defined x as that and simultaneously as that. Yeah, the train is moving at the speed of light. It has to be. Oh, can't be right. Can't be right. No, it can't be. He's gone wrong. He's gone very badly wrong. But this is the foundation for the equations I showed you earlier. It still works. Now, Einstein said that showed an object reducing in length. It can't, because that's based purely on Newton, and that doesn't happen in Newton's universe. It's not a pure form of Newton. As I said, Einstein's made a number of some slight silly mistakes, but it's as near Newton as anything else. It certainly has nothing to do with Einstein's new theoretical theory. And that is what Einstein says shows time slowing down. Well, it can't, because again, we're in Newton's universe, not Einstein's, and time doesn't change. What about that? Does that show nothing can travel faster than the speed of light? Take a guess. No. What he's got is a purely Newtonian pair of formulas, not correct, but they are Newtonian in as much as they're anything at all, and they deal with the perfectly normal Newtonian situation where two objects are moving relative to each other. Purely normal Newton. One of the objects just happens to be light. Yeah, that's important, up to a point. Let's change the example away from Einstein's train and light. So imagine you're travelling in a car along a nice, flat, straight motorway. No traffic in front of you. Yeah, I know, this is fantasy land. But you're travelling at velocity v in a straight line along this nice, flat, empty motorway. But there's a car right behind you, wants to overtake. Is it going to be able to overtake you? If it's travelling faster than you are, yes. If it's not, no. If it's travelling at the same speed as you are, it'll say where it is, glued effectively on your back bumper. If you're travelling faster than it is, you'll pull away from it. Only if it is travelling faster than you can it pass. Okay? Fine. In this particular example, the back car is light. Light. What this is actually saying is not that nothing can move faster than light. This is relating to light's ability to pass a moving object. Why is that significant? Our eyes depend on light to see by. I can't see anybody out there, and that suits me fine. I'm not being rude, but it improves my confidence no end. I can't see you, but I believe you're still there, because I haven't heard anyone run for the exits yet. I can't see an object that's moving away from me at or above the speed of light, because light can't catch it. All right? For me to see an object, light has to catch it, pass it, come back to my eye. Activate the back of the eye, send a message up the optic nerve, and the brain says, "Cool, look at that." If the object's travelling too fast, light can't pass. The apparent limit that Einstein saw here has got nothing whatsoever to do with the object's ability or otherwise to travel faster than light. It's about light passing. And if the object is travelling too fast, light can't pass. Okay. Nothing there that says the object can't travel as fast as it likes, and nothing in anything Einstein ever does shows that it has got a limit. That's the only thing. And he's misunderstood it. Okay, back to our two-car situation. Let's suppose the car behind you is travelling faster than you are. It's going to be able to pass. Right. This represents your car. I'm not going to make it move because my arm gets tired. Here comes the back car. It's now going faster than you are. It will be able to get past. But how long will it take to get past? This is moving in Newtonian motion, so it is in relative motion to the other thing. How long it takes to pass depends on how closely the two motions match. Imagine it being a real car trying to overtake you. The more nearly your speed matches, the slower it is in getting by. Yeah? That's what's happening here. Here comes light. There's your car moving at V. Here comes light. If light is a lot faster than you are, it's gone. But if your speed almost matches that of light, oh, light's going to pass. It's struggling. Come on, guys, move, move, move. Light's going to pass. The more nearly your two speeds match, the slower light is in getting past. It's not that time is slowing down for the object. That relates to light slowing down in its progress against the moving object. What about the first one? Length. That ain't right either. Here we go again. There's your car. Here comes light. It's going to pass. It's going to pass. It's moving faster than you are. In any chunk of time, what gain will it make against your length? If its speed is a lot more than yours, it'll zip past the whole thing. But if your speeds nearly match, maybe it'll only get that far. Or if your speeds are even more of a match, maybe only that far. Or only that far. That relates to the gain light makes. Nothing to do with the length of the object. Nothing to do with the length of the object. Einstein has misread the whole thing. Oh, but he's Einstein. Come on, dear. What does a superannuated old bat like you who thinks she knows against Einstein? Okay. Just a sec. Let's make a bit of space here. Einstein says in another chapter of that book that that is the equation you use to demonstrate that an object in motion loses length. And to illustrate that, he says, let's take a solid measuring rod. There's the track. There's the train. A solid measuring rod, doesn't matter what the unit is, it could be a mile, it could be a metre, it could be a yard. We're going to place one end of this measuring rod, says Einstein, x bar equals 0, there. And the other end of this unit-long measuring line is going to be at there. That, says Einstein, represents the length of the measuring rod. No, it doesn't. Hang on a bit. Oh, wait that again. If I keep flipping, that thing will fall over. That is nothing to do with length. That's distance travelled. because that and that are now Newtonian equations for motion. Okay? Equations of motion. Distance equals speed times equation, which means that's the distance travelled. Nothing to do with length, it's distance travelled. Does it surprise anybody that the distance an object travels varies with its speed? That's what that is doing. Einstein is wrong to say that is length, it's distance travelled. But he makes a bigger mistake, and to my mind, a really ludicrous one. He says he wants to work with this equation, and to simplify things, he's going to work at time zero. I'm all for simplifying equations. Suits me down to the ground. Except that, yeah, that does remove that. It's become zero, which leaves x. But x is defined as a Newtonian statement of motion, distance equals speed times time. At time zero, that is zero. Inevitably, by Einstein's own foundation equations. Which means, al old pal, you can't have x bar equals 1. And that is as bad and as basic and as schoolboyish an error as I've ever seen anybody make. Einstein makes it. I'll show you in that. And it's not the only mistake of that elementary nature he meant. Yes, Einstein was a genius, a very, very clever man, but he was accident-prone as a mathematician. He was, sadly, quite a poor mathematician. And unfortunately, he never doubted himself. I've been a mathematician for quite some time, and I know very well it's so easy to make a mistake in maths. If you can't conduct a physical experiment, you're stuck with pure maths. It's very, very easy to make a mistake and let a minus sign become a plus sign or forget a decimal point or something. And if you end up with what looks like a strange result, if you're a good mathematician, you don't say, oh, look what I've discovered. Instead, you say, oh, what have I gone wrong now? And you go back and check. And if you go back and check, the chances are you'll find what you did wrong. Einstein didn't do that. He never doubted himself enough. His lovely special relativity is nothing more than a slightly mucked about with version of Newton, which is, of course, why it tends to work-ish, because Newton works. But it is a mucked about version. So Einstein's theories are nothing more than that, a badly remembered dream of Newton. They're not right. Which means there's absolutely nothing to stop an object travelling as fast as it likes, because it can in Newton. There are no bars, as Einstein thought he'd found. That's not there. That doesn't exist. There's no limit to the motion of an object. There are loads and loads of engineering problems to be resolved. But then we've done that before, haven't we? Last century, if you go back to the start of the century, before Einstein was writing, aeroplanes were just about the stage of cylinder flap their wings for takeoff. But 50 years later, we had the jet plane, and we could send things faster than the speed of sound. Okay, light is 900,000 times faster than the speed of sound, but it's a start. And 60 years after the very start of that century, we sent men to the moon and back. If we want to, we can do it. If we want to. We might decide we don't want to. We might decide it's not worth it. But there could be things around us right now that are travelling faster than the speed of light. It might be what's at the heart of quantum mechanics, for example, the so-called quantum leap. It might be what's going on with a black hole. It might, I don't go into the UFO territory, but maybe it's the explanation for how they, if they, do it. Maybe they found the secret to faster than light travel. Don't know. I don't go there because that's not my subject. All I can say with certainty is there's no reason why not. If an object is moving faster than the speed of light, you will never see it. It's going too fast. If an object is travelling just below the speed of light, you will see it, but it's going to look weird because light is now struggling to get past and get back to your eye. In finish, I have just finished, you can all relax. I want to quote to you a nice little limerick. I don't know exactly who started it. It certainly wasn't me, not guilty, Your Honour. But it's been around at least since the 40s and possibly earlier. It runs like this. Have you heard of the family Stein? There's Gert and there's Epp and there's Ein. Gert writes books that are rude. Epp's statues are crude and nobody understands Ein. Perhaps you do now. Just a little bit. I have done.
Thank you, Patricia.